Good afternoon, everybody. Welcome to the sixth seminar in a series from the Melbourne Energy Institute MEInetwork24 Seminar series. This year, we're looking at the electricity system overall, and we started from one end, generation through transmission, distribution, wholesale markets, retail markets, so on and so forth, and we're now getting towards the consumer end of the system, looking today at distributed energy resources. My name is Michael Breer. I'm the director of the Melbourne Energy Institute, and I'll be introducing our speaker. I won't say guest speaker because he works here, but I'm introducing him nonetheless. Before we do so, I'll of course acknowledge the traditional owners of the lands on which this seminar is being given in person. We of course acknowledge the traditional owners of the lands. For those of you online, wherever you may be, the traditional owners here are the Wurundjeri, Wadawurrung and Bunurong people who've been custodians of these lands for thousands of years, and we acknowledge and pay respects to their elders past and present. Thanks all of you for coming along today. This is seminar number 6 in 7 seminars in total, so our second last one. As I mentioned before, we're getting towards the consumer end of the electricity system. I'd also like to invite you, those here and online, to the Melbourne Energy Institute Annual Symposium, which this year will be on the 22nd of November. That'll be held on campus again, and we're really delighted to have a bunch of terrific students and staff from this university speaking at it. This is in about 6 weeks' time, and also some distinguished people from elsewhere, including Anna Scarbeck, who's the CEO of the Climate Works Centre, who'll be our opening plenary speaker. So that's already online. Go to the MEI webpage. Just if you haven't got the MEI webpage at your fingertips, or you're not a subscriber already, just Google Melbourne Energy Institute. That'll come up, and register for that free in-person event. Food provided. Not that that's an incentive for graduate students, free food. I'd never suggest that. It is for academics like me, but not for students. Now, just a bit of housekeeping for today. If you have any questions, please enter them into the Q&A box, the chat, as we're not doing chat. And then at the end, if there's questions, we'll do our best to answer them. Now, I'll introduce our speaker for today, Professor Pierluigi Mancarella. Pierluigi works here and has done for about 8 years, professor in electrical engineering, and I think you will work out that Pierluigi by name is from Italy originally, but via the United Kingdom. So please welcome Pierluigi, and thank you all for coming along.
Thank you. Thanks, Michael. Yeah, good to see you. Okay, so this will be working fine, hopefully. All right, thanks again, Michael, for the kind introduction. So what we're going to cover today in the next probably 40 minutes is a little bit of an overview of the transformation that we're seeing, particularly in Australia, with regards to distributed energy resources and different means to try to integrate these resources into the power system and the market. So, of course, let me start with some historical perspective on what we've seen in terms of system balancing. We've relied historically on conventional power plants pretty much to provide system balancing, and the demand side has been inflexible in most cases. Of course, now we're really seeing different changes that I will outline later. Now, if you look at this from the point of view of flexibility and the kind of architecture that we're seeing in power systems, then there's been direction from transmission system. Effectively, flexibility has been historically provided by a few hundreds of large-scale conventional generators connected to a transmission grid to a distribution grid where all consumers are, and what the demand is really, there's largely inflexible in the sense that consumer would just expect to consume energy when they need it, and there will be no real interaction with the rest of the grid and the market. So if you take this from a very basic kind of market sketch, what will happen is that a typical supply curve like this one, effectively see that there will be generators more like increasingly more expensive trying to supply a certain level of demand. So here you see the prices, here you see the level of demand, and with time you will need to somehow cover that demand curve that you see there. And say, okay, we start with a low demand level, and then because there would be somehow intersection between demand, they effectively on the sketch is a vertical line because it is basically not price responsive, certain level of price. Then moving forward, demand increases, you got now to the middle of the day, prices become slightly higher, and then you go to peak times, and again, because of the nonlinearity of the supply curve, it's like having all the peak generators, particularly gas turbines, diesel generators, and so on, playing a certain role, and then prices become higher and higher, and everyone eventually pays the market price. So all generators are, regardless of what they actually bid, regardless of how much they cost. So these relatively cheap generators will still get the market price when at peak times when again there will be a few very expensive generators operating. So that's how historically we run process. Well, historically we still running pretty much like this. So this is really the sketch, realistic sketch of what is happening in the market in Australia as we speak, effectively. Now, as I said, that kind of demand curve is basically vertical. It changes with time because the amount of power that is required by demand changes, but it's not price responsive. So it's in technical terms, in economic terms, it means that it is inelastic. There is no responsiveness to prices. How have we justified this historically? Well, fundamentally the fact that electricity has always been considered indispensable. Somehow we always thought will always be available. In most cases, is not such a big proportion of total cost. And say, well, actually, we don't really bother somehow. The pricing may be a little bit higher than they should. However, there is a time when actually we should bother. I'll show how we should actually mind more and more about this, because a little bit of demand response active in the market even now could actually bring extreme benefits, very, very significant, particularly when conditions are a little bit not normal, again, extreme conditions. Just for the sake of definition, by demand response, I mean the ability of adapting the consumption profile to respond to some form of price signals. So when you look at, for example, a very hot day, what will happen in the market sketch is that it would be a little bit higher demand up there. And then because of the higher demand, effectively, you would see an increase in your inelastic demand. And as you can see, there is like to the point that you might even miss somehow intersection between supply and demand. So prices literally go through the roof. And that's when, in many cases, actually, we need to operate at a price cap. Eventually, there is a capacity scarcity somehow, and then we basically need to operate really with all the possible resources that we see in the grid. Very similar things, however, a similar thing will not happen if we could, for example, provide a little bit of demand response. So with a few relatively small amounts of demand response, so with some loads, wherever they are, aggregation loads available in the grid saying, well, actually, prices are so high, I really don't want to pay that money. Maybe I will just disconnect or reduce my consumption instead. Then the equivalent effect in market sketch will be something like this. So guess what happens? Actually, the ones really benefiting is basically everyone. Because clearly you see that before you were even missing intersection between supply and demand, so prices eventually would be very, very high. When I say high, I mean, if you look at average prices in the grid, we talk about in the order of $100 to $300 per megawatt hour, and is already relatively high. Then when we talk about the market, the price cap, which is what we see when there is capacity scarcity, then we talk in the order of $15,000 per megawatt hour. So we talk about like basically two orders of magnitude bigger. Now, with a little bit of demand response, you basically come back into the space of very normal prices. Of course, again, in this case, everyone will pay much lower prices. And of course, all consumers will benefit. Well, all consumers, of course, not the suppliers. The suppliers are very happy to charge very high prices, of course. Same actually happens when you have outages in interconnectors or generators. Effectively, depending where you are in the grid, whether there is some generation failures, maybe some interconnector and so on, the equivalent effect would be to have a supply curve that somehow shifted towards the left because there is some capacity is no longer available. And again, you run the same situation as before, where prices may actually become very, very high. And that's exactly what we see happening now. Again, with a little bit of demand response, so flexible loads available to disconnect or use the demand when there is really a need to do that. Again, prices could become much, much lower, and again, everyone would benefit. So say, well, why don't we do it? I mean, I'm sure that everyone would agree that, at least from the consumer's perspective, it's a very good idea. Well, now foregoing consumption, it's not always possible, maybe just for a few activities. And then shifting consumption is only possible really if there is some storage in some different form. Okay, let me tell you a little bit more about storage. For example, when you look at this table here, that I usually I use also as for exam questions. So I would like to ask you, if you look at this kind of appliances, which is what we have at home normally, how would you consider this? Would you consider them non-flexible, flexible, deferrable, so you can shift them in time? Would they be considered curtailable? So can you curtail the consumption partially, fully? How would you consider that? For example, a TV, is it deferrable? Is it curtailable from electricity perspective, and then from consumers' perspective? Would you curtail? No, you will not switch off your TV. They give you $50 for next hour not to watch Netflix. You wouldn't do it.
These appliances have big differences in their.
Yeah, that's why I'm showing this. Of course, they have. That's exactly the point of showing there is a diversity of usage. So if for $50 for next hour, yeah, I know. So would you switch off your PlayStation? Yeah, that is exactly the point, right? So that is exactly the point. So that's like, eventually, if you when you will be available to switch off your demand or move your demand and so on, that you always have some form of storage. For example, if you travel a lot like me and you need to wash your clothes back from a trip, you need to go again on a trip. And if you receive a signal say, oh, you can't wash your clothes because it's too expensive. I'm like, okay, wait a second. Do I have like huge number of t-shirts available or not? Because I'm leaving in 2 hours. So if I have it, eventually I have a huge store of t-shirts. Therefore, actually, I can forego consumption. So it is the story of my clothes that actually enable me potentially to accept the demand response signal. It's the same if you invite someone at dinner and then suddenly you realize that actually you do not have dishes, clean dishes at least. It may be very expensive because there is an outage on generator in your local area. Again, if you have quite a good store of clean dishes, actually, you don't bother. And it's okay, it doesn't matter. I will do the dishes later because it's too expensive to do it now. Of course, you can always do it by hand, but no, that's a different story. So there is always some form of storage somehow available when you allow some flexibility in demand. As Michael was saying, when would you not allow flexibility in demand? Well, for everything that you can store, and there are a few things that it's not really easy to store. This is like one of my nightmare in a way, but also one of the greatest emotions. I don't know now. Some of you, well, many of you will not have born, but been born. Yeah, that's budget. Yes. And you remember? Do you remember this? You were too young. Yeah. So yeah, this was 1994 final of football soccer between Brazil and Italy. And this is the last penalty of the penalty kicks, and Baggio missing that, and Italy lost, right? So how can you tell anyone, switch off the TV because it's too expensive, don't watch the penalty kick in Italy? Well, so what I'm trying to tell you is that actually flexibility, demand response does not have anything to do with technology, nothing. It's only had to do with consumers. So fundamentally, we need to rethink the way of, say, the technology, especially as engineering. I mean, technology. Effectively, has got to do a lot with actually what technology can enable for consumers. However, things I'll change it a little bit. because some technologies will actually enable you as consumers to access more and more storage. Remember that fundamentally you only shift demand if you have some form of storage. So the game changer here is actually electrification, because the moment that the more you electrify on the demand side, the more you have some form of storage available. For example, you have storage in hot water or water heaters, you have storage in thermal inertial buildings, you have mobile storage in electric vehicles. And eventually, because you cannot access so much storage in different forms, eventually you can shift your consumption. Therefore, you can potentially provide somehow benefits to the grid and to the market. So somehow we shouldn't worry too much about, or we cannot forego consumption, or we don't have storage. We do have it, but then we're still missing something. What is this? Well, the fact that when we look really at the very nice dynamics that we see in the markets, that's all happening in the wholesale market, in the wholesale side of the market, where actually all large generators somehow play the game. Eventually, most of demand, happens really at the lower level. Like most of us eventually would consume electricity at the level of the retail side. And what do we see on the retail side? So what do we see on our bills eventually? Well, that's what I see. My bill, this is my bill. You probably recognize also the retailer rates. And what I see here is that I pay a certain amount per day. It's about $1 per day. And then I pay something like 20 cents per kilowatt hour. It's a flat tariff. So whatever I consume, whatever time I consume, that's what I pay. Why should I be flexible? What happens if I am flexible? I'm still paying $1 a day. And whether I consume now, I consume in 2 hours, or I consume tomorrow, I'm still consuming those 2 or 3 kilowatt hour that, for example, for whatever usage. So why should I be flexible? How do I see somehow that in the market there is an outage, there is the prices are going through the roof? I just can't see it. We don't have any visibility of that. So the fact that we have a flat rate tariff system that not only us, I mean pretty much around the world, actually reinforcing this issue of the pricing elasticity. So the fact that demand is not responsive to price. Well, much demand, most of demand actually is not even exposed to prices. I mean, how can you expect that anything would happen? So what else is then needed to really unlock this demand side flexibility? Well, clearly you need some form of pricing at the retail side, some dynamic or time varying retail pricing. So you can see somehow that something is happening in the grid, in the market, and you can contribute. So you got the incentive, for example, to consume energy when it's cheap, more energy when it's cheap, and not to consume when it's expensive. And of course, ideally, we'll also need some smart meters. There is some way of doing without smart meters, but it would be very difficult. So technology actually helps because smart meters enables you to see dynamic prices. And then on the consumption side, the more you electrify, the more you have access to forms of storage that would enable you to shift demand. Now, how is what is the, because we have such a fast changing grid, what does the future look like? Are we going to see more demand side flexibility? Are we going to need more demand side flexibility or not? Well, if you look at what IEMO is somehow envisaging that might happen in the integrated system plan, one of the scenarios, the most likely scenario is called the step change. We see effectively down there is a small red star there. The demand side participation is actually probably very, very tiny when you look at the system level interaction of demand and the rest of the grid. At the same time, we have a gigantic amount of rooftop solar that is coming to grid, where it's already there in large parts of Australia. You also have a very significant amount of so-called CR, consumer energy resources, I will mention in a second, in the form of storage. So all of that is actually connected to the distribution grid and is somehow orchestrated, coordinated to interact with the transmission grid and you can imagine with the market. Now, when you look at this kind of thing, say, well, is it going to be big or not? But should we need it in general? Is it something good to have, and should we need more of that? But in order to understand this, we need to go back to our market sketch and say, well, what happens actually when you start having lots of renewables in this grid? Because so far, you see, I didn't really tell you what this supply curve would be made of, but eventually you can imagine that it would be fundamentally coal generator, gas generators, and so on. What happens when you have renewables in the grid? You have the so-called merit order effect, because renewables are very, very cheap in operational terms. They will come basically with zero cost, that dollars per megawatt hour. So when you have a little bit of renewables, so when you have no renewables, variable renewable energy, as is good to say, that will be the sketch. And then you say, well, I start having a little bit of renewables. Because they are a zero marginal cost, then they come from the left and they push the supply curve a little bit. And so, okay, let's have a little bit more. And that's a price that you get. So what is the immediate effect that you can see? With a little bit of renewables, the prices have already gone down significantly because of the shift of the supply curve and how steep the supply curve is when it comes particularly to high load levels. And so where we have more renewables and the prices are even lower, and then eventually say this was for the high demand. What happens for the medium demand? Well, again, you have prices that are overall much lower, and for the low demand, prices are again much lower. But you would understand that having no renewables, high renewables, low renewables, is not only a matter of how much you build, but it's also a matter of how much wind, how much sun you have in the grid. So effectively, what happens is that depending on the amount, so before, effectively, without renewables, you always have one supply curve, somehow constant for most of the time, and then demand would drive the price formation. Now, with more and more renewables, effectively, is not more just demand, actually probably not so much at all, is really how much sun and wind you have in the grid, because how much sun and wind you have in the grid operationally, besides how much you have built, will determine whether you are in this toy example here on the no renewables, low renewables, or high renewables case. So you really, and as a consequence, of course, you introduce huge price volatility in the market. And of course, you are still sitting there with a flat tariff. You don't see anything, whether it's today or whether it's in 10 years or 10 years ago. In the meantime, the market's changed completely, and all these generators or retailers are somehow playing a completely different game. At some point, what happens is that there is so much renewables in the grid that effectively they would produce so much energy. And because you may also have some generators, they are inflexible still, like coal generators and so on. Eventually, there will be part of the supply curve that actually will bid negative prices. That basically it's a sign to say, I cannot switch off. For example, a coal power plant, I am inflexible, I am running, I cannot switch off. So I will bid the negative price to say I will stay on no matter what. So when you look at, again, this toy example, you end up actually having negative prices. So you have a relatively low level of demand, and you start seeing negative prices in the grid because there is so much renewables and there is also some inflexible generation. Now, all of this on the supply side, but actually on the demand side, there is also another game changer that I've not mentioned yet, but you would have seen coming from the very beginning, of course. Rooftop PV. So how do you, what is that, how would that supply demand curve change with rooftop PV? Why am I working now on the demand curve and not on the supply curve? Because eventually what happens the way that the current market and system operates, you are not capable to see all this distributed generation in the grid. All you are capable to see is the net demand from the transmission grid and the wholesale market. So effectively it would be the actual demand minus the local generation. So that demand effectively would be what happens when you have rooftop PV, but it's a typical Melbourne day, so it's like gray and rainy. Okay, so this might have happened yesterday. So what's happening today compared to yesterday? Well, eventually today, even in Melbourne, start seeing lots of sun. That demand that you see at the middle of the day is no longer there. It's got this very nice shape that altogether is called duck curve internationally, although in Australia doesn't look like a duck because it's Australia. So it's got all the strange animals, as you know. And then, so here you got the duck curve, and eventually you end up with a demand in the middle of the day that is basically lower potentially than during the night. But it's the net demand, is demand minus the local generation. So that's what you have when it's sunny in Melbourne. So yesterday you had the previous demand, and now same time, but with sun, you have a completely different demand and negative prices. Then everyone will say, well, hooray, that's what we want. More negative prices for everyone, for us consumers, and we will save money. Well, I'm not sure that anything is happening anyway, because you're still paying a flat tariff, and I don't see any negative price. I don't know you. So eventually, is it really so? Is this model working well for anyone, including customers? Well, that's the picture what's going on pretty much every day in South Australia when it's not a peak time and when there is lots of renewables in the grid. So systematically, eventually, there is during the day negative prices because there is too much sun eventually, and of course there is wind all the time. And then during the evening, when there is not so much sun, then all the generators will start bidding, the conventional generators, to supply the higher demand. And in some cases, they will start bidding higher than they would because they are producing so much less energy during the day that they still need to recover lots of fixed costs. So eventually, we see not only the prices that are more volatile because of the sketch that I showed you before, but also because when there is an opportunity for conventional generators to recover the fixed costs, they would actually start bidding higher than before, and therefore we start seeing really a huge range of negative prices where there's lots of renewables and very, very high prices where there is not many renewables. Again, this is all kind of, this is like trivial, I would say, power system economics, the theory, but actually we see this in markets. But what is not so visible, again, to consumers in particular, is the fact that when this happens, it's got a huge impact on other renewables. So, in fact, this is a week, or which week was that? About a year ago. So this was the week when there were big announcements. Effectively, South Australia was running on a close to basically 100% renewable net energy across 1 week. At the same time, basically 450 megawatts of large-scale solar was being curtailed. So effectively, South Australia was running on rooftop PV, and all large-scale solar was being curtailed. Say, okay, why is that happening? Okay, there is so much renewables. Rooftop PV are not part of the market. They're not visible. Prices go negative because of the market formation sketch I show you. Large-scale renewables are exposed to negative prices, and they go into so-called economic curtailment. It doesn't make sense for them to produce because they will have to pay to produce, and then they go for self-curtailment. And they should, because we need to balance the grid. That's why we have negative prices. But you see here that you have all this rooftop PV pushing, not seeing prices, nothing, and pushing energy into the grid. At the same time, basically the same technology at transmission level being curtailed. And effectively, the amount of wind and solar that was curtailed at a certain point was 125%. So basically 100% was covered by renewables, and additional 125% was being curtailed. So effectively, we are running the grid by curtailing a huge amount of renewables because somehow there is a lot on the supply side, there is a lot on the demand side, and there is a clear disconnect between what is happening in one direction and on one side and another. And somehow this is really the problem of a kind of fit and forget paradigm when we talk about distributed energy resources, because eventually say, well, you just connect rooftop PV, electric vehicles, whatever, don't worry about it, just someone else will take care of that. Eventually, you end up with all this embedded generation, but embedded resources in general, that are not dispatchable, not controllable, not visible to the grid and to the market. Locally, at the same time, when you start taking your rooftop PV, again, they're all generating electricity at the same time. So you will end up overloading transformers and lines, because of thermal limits or voltage limits. So eventually there will also be a need somehow locally to manage these renewables. So locally, all this rooftop PV is creating some issues that need to be managed. At the system level, the interaction between supply and demand means that you are curtailing lots of renewable energy. Well, there must be something smarter that we can do, right, moving forward. We cannot just say, well, we built everything, we gave money to build rooftop PV, we are supporting large-scale renewables, and somehow nothing is happening. But the way forward is that while in the future we start seeing all these conventional generators disappearing and more renewables coming to the grid, we need to realize that maybe we should not only talk about large-scale batteries and pumped hydro, but there are actually huge opportunities, as I mentioned before, in the fact that we are installing more and more flexible distributed energy resources on the demand side, where there are actually huge opportunities. So what are these distributed energy resources? How do we move from what I called before demand response to distributed energy resources to then what is more recently called consumers' energy resources, CR? Well, eventually, this is really coming from rooftop PV and electrification. It's really like the dawn in the world. Australia is really showing the way to the world. Maybe only California has got some comparable terms, I would say. It's really showing what it means to have lots of DR in the grid, where DR is now distributed generation, think of rooftop PV, demand response, think of your all your appliances you can have at home, and then different forms of storage. Think of batteries, think of water heaters, think of electric vehicles, and so on. And many of these resources are behind the meter. They are at home. Actually, they belong to consumers. Consumers are becoming prosumers, producers and consumers. These are the consumer energy resources, CR, where you really highlight the fact that they belong to the consumers. And in fact, as I showed you earlier, much of this flexibility really depends on what the consumers want to do, especially if there is not much storage in that. So when I look back at what I was seeing there, actually, there are really great opportunities if you look at flexibility perspectives from what those distributed energy resources could do. To a large extent, actually, I really think that these benefits are being understated. And there are actually, the opportunities can be much bigger, and that's why somehow I'm also showing this in this lecture. When you look then at the historical perspective of saying large-scale generators provide flexibility to the demand side that is inflexible, moving forward in the future, what is happening is that the transmission grid with more renewables is becoming less flexible. Actually, it needs to be balanced because of the variability and uncertainty in renewables. At the same time, you start having lots of distributed resources that, because of storage, potentially can be controlled and can be used to balance the larger grid. That's why we start talking about all these aggregation techniques, like virtual power plants, energy communities, microgrids, that somehow could provide benefits to the grid by providing flexibility and again balancing the system. So why would you build more and more large-scale storage pumped hydro when actually you have lots of storage that is distributed, can help you with rooftop PV, can reduce prices locally, and eventually can create a grid that is cheaper for everyone? Because to do that, you also need someone that takes care of what is happening in distribution network to manage all the interactions at distribution level. That's why we talk about a distribution system operator. We no longer talk about a distribution network operator, what is known in Australia as distribution network service provider, because now this is really an active system to be managed, and then we need a distribution system operator, the same as we have a transmission system operator in the transmission grid. So how do we transform a grid, distribution grid that was passive, to a grid that is not that it is now active and potentially needs to be controlled. Well, there are different ways of doing it. What is clear is that somehow we need to move through complexity, depending on how much distributed energy resources we have. Effectively, you can think that for low penetration level, low density, you can deal with the basic standards and some form of connection agreements. And then with more and more distributed energy resources, you need to incentivize operation of DR by some form of dynamic pricing, so time varying pricing. And then moving forward, perhaps you need something more advanced, so some form of flexibility markers, local flexibility markers. There's been some experiment here in Australia, lots going on in Europe with not great results, I'd say, but still, no, there's a lot that is happening. And of course, the more you build complexity, especially because it's needed with more and more distributed resources in the grid, the more hopefully you will be able to actually access value from these distributed energy resources. Now, and there will be other parameters, of course, that will play a role. Now, if you ask me where I think we are, particularly in Australia, and we are better, I mean, probably not the most advanced in the world to a large extent. I think we're still in the region there, and probably we're moving soon towards this region from the point of view of saying we really need some more dynamic, active pricing, for example, in the grid to really drive a new better operation. At the same time, there are lots of discussions about maybe you can have third parties, so not necessarily by some form of pricing, but having third parties that are bringing together this DR and make them participate in system operation. You know, the famous virtual power plants, where effectively it's like they would aggregate highly distributed resources to play in the grid and the market as an equivalent power plant. Just as not a big combined cycle gas turbine or just a number of, for example, aggregated batteries. So the interesting thing is that when you look at that and say, well, what is actually the equivalent that I see from a transmission market perspective of lots of distributed batteries? Well, one convenient way, this is slightly technical, but it's more the message that I need to get. One convenient way of showing this is say, what are actually the regions of operation of all these resources when I look at active and reactive power? Reactive power is something that's useful to deal with the voltages in distribution networks, in non-technical terms. Well, you have regions, and those regions eventually would describe the flexibility of your resources. You can imagine that the larger is a region, the more you can operate in different parts of a grid, therefore the more flexibility there is available to interact with the rest of the grid. And then the question is, if you take 3 small regions like this and you sum them, what is the equivalent region? How do you sum this? Well, turns out that when you sum it, it will become something like this, and you can do the maths. And the maths will tell you that 1 + 1 is greater than 2. So there is some magic that happens there, and it can be explained mathematically. There is some magic that happens there, say that I got to flexibility regions, I have more flexibility regions, I put them all together, and the equivalent of flexibility regions is actually much bigger than the sum of the individual regions. So there is a benefit that is emerging, that we call the benefit of aggregation, especially then if you can actively control this, we call benefit of orchestration, that actually you cannot see if you take these resources individually. So you can try to create a pricing for these resources, but still there are benefits when you aggregate and orchestrate that you will not be able to access unless you do something else that potentially could be done through these virtual power plants. And then eventually, what will happen is that you end up with some form of aggregated regions like this one, and then say, well, when there is lots of renewable energy in the grid, I will try to have all my resources buy energy from the grid, especially somehow there is someone helping this virtual power plant doing something for you. And when prices are really high, I can start selling perhaps the energy from my battery from the grid. And then you remember that was mentioned before that there is now a system operator also locally would say, wait a second, actually you cannot buy and sell as much as you want, because the grid is actually finite. So I need to introduce some formal constraints in my grid that tells to the resources, you cannot do whatever you want from a commercial perspective, like a virtual power plant would do, but you need to consider the local network limits. So you end up with what we call the feasible operating region. That is effectively what is happening now when we talk about import and export limits and dynamic operating envelopes. So all this discussion that you may have heard of when we talk about limiting resources, import and export at the distribution grid is equivalent to say in these regions where we want to pursue some commercial objectives in buying and selling energy, well, we will need to limit what we want to do because of the physics of the grid. And not only that, because at some point, we've seen this in South Australia a few years ago, there may also be a need to disconnect some of these resources, the same as we disconnected resources in the transmission grid when there is a need to do that. We do this economically, but we also do this for security purposes. We should try to avoid situations like this, where effectively, because this rooftop PV was not visible to the grid, and because it was putting at risk actually the security of South Australia, particularly when it was operating islanded for some time, then there was a requirement somehow to basically go around and disconnect PV. Now, I will tell you later how this can be, how this was done. This is a classical, again, exam question, actually. How can you disconnect 2 million PV panels from Adelaide, basically in a matter of a few minutes? So eventually what happens is that in this kind of looking forward, you might actually need to also disconnect to limit even further the production of this distributed generator because of security purposes. And we'll be able to do this possibly via, again, these distribution system operators, by the use potentially of dynamic operating envelopes. They're not only taking care of what is happening at the distribution level because of voltages, for example, or local overloading, but also the system perspective somehow, potential issues they might create. Now let me skip a few things here because I wanted to mention something else, which is not only, of course, how you do things by aggregating through virtual power plants, but you can extract benefits in different ways. For example, you can extract benefits from communities. If you take a scheme like this, so okay, how flexible is a scheme like this, and how much can I share some potential benefits with my neighbors? I think imagine a scheme like this were actually allowed to kind of commercially, I mean, physically, of course, you can exchange power, but can you do it actually properly commercially? And then if you have a bunch of rooftop PV and batteries, and now they are allowed to trade with each other, what can you achieve technically and commercially? And then eventually, what can you achieve on a scheme like this? If you live in a building, you cannot build, don't have space for a rooftop, you don't have space for a battery. Do you need to give up? You cannot participate in this transition. Can't you? You cannot help. You cannot interact with your neighbors. Well, that is actually the idea of community energy systems, where, for example, we start relying on community batteries and community level resources to actually bring significant benefits to the system and also to your neighbors. And then here in the audience, I can see Carmen. Carmen will tell you at the next seminar more about this. So one of the projects that we worked on is actually this Power Melbourne project. It was like a fantastic project with the city of Melbourne, where effectively it was about understanding how a network of community batteries, so eventually a virtual power plants of energy communities could actually be optimized in terms of operation. Then how can you build a business case actually for this to happen? So it's interesting how effectively when you start operating with kind of schemes, you can get both, the best of both worlds somehow. There is some benefits that you can get if you operate, because you operate behind the meter. There is some benefit because you operate so-called in front of the meter, effectively meaning that you can access different value streams when when you do that. Again, don't miss the next seminar, because I'm sure the camera will tell you a lot more about that. And then the last point I wanted to cover is in this change that I'm showing here, in the system I'm showing here with massive changes from one grid to another, we moved fundamentally from a system with no flexibility on the demand side to a system with lots of flexibility on the demand side. Then the question is, how much redundancy, network redundancy, do I still need in the grid? Because in the past, because the system of the past was inflexible on the demand side, I had to build a huge grid on distribution side to supply my demand. But now what will happen if I can flex my demand? Maybe I do not need all the network, because now I can actually modulate my consumption and in case also production locally. And if you look at the bill and how much we pay for network cost, there is actually a huge opportunity to displace network cost if you are able to intelligently move away from the kind of current schemes in which one method is really to build the networks. And in fact, it can be demonstrated that the moment you want to start using, for example, microgrids and distributed resources to displace a network, actually there is a very significant benefit. You no longer need so much redundancy. We call it, for example, -1 redundancy. Basically, you double the amount of network that you need. And on top of that, you can also create a resilience to the grid. So there is an outage on the network, especially if you are far away from the main grid, rural areas and so on. Well, you start using distributed resources aggregated in microgrids that can effectively, they are like the same as communities, but can get off grid if needed, so they can actually operate as an island, and then bring again significant benefits to the grid because they disconnect if needed, effectively providing some form of demand response, but also locally because you can keep the local system running even after significant outages, wildfires, and so on. In fact, this is really for me where the elephant in the room somehow, because that's what is stopping us from doing lots of things. The fact that at the moment we're not clearly able to build. This is a very interesting paper. I'm happy to share with anyone if interested. You cannot really build more distributed resources to deal with bushfires, not because it doesn't make sense to do that, because the regulatory environment does not clearly recognize the value of doing that and the risk actually of outages for the communities. So there is a little bit of rethinking of what is happening there in the regulatory environment. And of course, the next next step would be, if there is a value of DR in displacing grid, at what level is DR displacing grid? Is it displacing at a distribution network only, or is it displacing the transmission level too? Because so far, for the ones who are familiar with that, the integrated system plan of IMO really looked particularly into transmission grids. But and then in a classical passive distribution network, you would just build more and more lines. I highlighted there the lines in red. But maybe if you start having an active grid that actively participates in providing demand response was needed, including there are, for example, network congestions and so on, so that you do not need potentially to build more grids, including the transmission level, perhaps you can start using more and more of the active resources in your distribution grid and build less transmission. In fact, what we're already seeing in our initial work we've done this somehow, that the more you can control DR, the more you can reduce investment. It can also actually reduce the uncertainty that you will see in the large-scale investments, and you could actually enable more robust paths. So eventually, DR allows you to build better systems with less uncertainty, and somehow you will build a less transmission grid and more and more distributed resources. But at the moment, somehow the regulatory environment does not really allow us to understand all the benefits. Of course, moving forward, then one would say, if DR is actually to take all this active role and providing lots of benefits and services, well, should it be remunerated for services that really we don't talk about now, including some form of resilient services, or maybe is it more like a social responsibility? And there are lots of active discussions. I invite you to read some of these papers by Nijlal, that works with AIMO, and is great great thinker in this kind of space. So really interesting discussions. So just to conclude, I think it's clear that we are looking to a future that is completely different, and looking at distributed resources that are kind of bring a revolution, same as Edison did, in 1878, when he said we make electricity so cheap that only the rich will burn candles. So we'll see, we're getting there. I think rooftop PV is close to, the cost is close to zero. The only problem is that the value is negative in the market. This is really what is happening. So we need to understand how we need to really bring the balance back, try to empower more consumers and distributed resources by doing the right thing and providing the right incentives, and maybe in the short term just build more storage rather than more rooftop PV to make all of this happen, really. Thank you. Thanks, Michael.
Thanks, everyone. Oh, you got the questions there? Encourage those online to send some questions in through the chat. No, through the Q&A, not the chat. And those in the room, put your hand up. You don't need to get online. So fire away. Yes, sir.
Just a question about
Actually, so the people online can hear you, if you could just hold off and speak into the mic.
just a question about the cost of batteries. They seem to have been coming down, and they appear to be coming down even faster. So what do you envision in another 5 years with respect to batteries in the home? At the moment, I think something like 3 to 5% of the people that have solar panels have batteries at the moment. So how is that going to start to change how the individual demand is going to happen?
Yeah, no, very good question. Thank you. So I would hope that we have more and more of them. The problem is that we do not have the right incentives to do that. So if large part of my presentation was really to say, the more we try to be cost reflective, what happens in the system, in the market, towards the consumers, the more the consumers will be incentivized to do the right thing. Now, with the flat tariff, fundamentally, we see there's not much incentive. And even with rooftop PV, we basically say, well, we consume less energy. There is an incentive to that. We pay less. However, it's very different from, say, imagine now you have a battery and you store energy during the day when, again, in the market, there is no value in injecting more energy. And then during the night, you start competing with the open cycle gas turbines by injecting energy back. So with a little bit of time varying prices, you can actually create some incentives that, given the way that the prices are going, could be enough to incentivize consumers to make the step. And otherwise, I think also the government probably should step in and create a little bit more flexibility in that direction.
The most recent ruling by the Essential Services Committee has put together a time of day fit rate, and they have two of them actually, one depending on if you go for option 1 or option 2 or something like that. So they are starting to move toward a TOD fit rate actually. So
and it's great. It's a great step. It's a great step further. Unfortunately, the pricing, this is a very complex topic. It's like, because it's like there is pricing that you will see somehow that should be reflecting what is happening in the energy market. Then there is a pricing that should be reflecting what is happening in the network. And then eventually the retailers at the moment, give you a package where they say, well, this is what we see in the market. That's what we're giving from the network. That's what we give you, which is very different eventually. So the kind of how the pricing is aggregated across the grid and how retailers can do the right thing is a very big topic. And again, probably there will be more work that is needed in that direction.
Great. I'll alternate online and in person. So I'll take an online question. I will first say that there's a very effusive thank you from one person whom we know. Won't name them, but that's a very nice thing on a terrific presentation. A couple of questions though, which are interesting around regulation. So I think I'll kill a couple of birds with one stone here. Can we describe the assumptions that need to change to ensure the regulations reflect the new reality of the DER you have just described?
Yep. So effectively, there is it can be slightly technical the way that is pursued, but eventually the answer is we have a methodology that is fundamentally deterministic. We cannot capture the value of DR in a deterministic setting. Effectively, the big value is in the fact that there is lots of uncertainty in the developments that we see. Every time that we build more network, we lock into something that will be basically there forever, potentially asset that we don't need, stranded. Every time that we use intelligently DR to avoid that investment, we create value that in the long term can be very significant. However, we have demonstrated this from work years ago in the UK. The current framework that is deterministic does not allow you to actually value DR properly, and that is the very first step to be made.
Good. Okay, one from in the room. Yes. Oh, hang on. Sorry, wait for your microphone.
Thank you. Yeah, thank you for the talk. I was just wondering that with the reactive power chart that you showed and how 1 + 1 is more than 2. That was news to me. Can you elaborate a bit more on the nature of those benefits?
Yeah, effectively, it's new to many. It's pretty technical. So, well, mathematically, you can see why that happens, because it's you sum across a geometric space somehow. You do not sum arithmetically eventually. So technically, it's called Minkowski summation. What happens mathematically? In practice, what it means is that if you look at the space, the operational space that you can cover individually with resources that you do not really aggregate together and coordinate together. If you look, from outside, there will be only a region, certain regions that you can cover. The moment that you can coordinate them, you will be able to cover regions that individually you will not be able to see or aggregate. So you still see the aggregate, but because you not coordinate them properly, there are areas of the kind of map that you are not able to operate in.
There's only 2 minutes left before 4 o'clock, so we have to wrap up. I'm sorry, there's plenty more questions online. I'm sure there are more questions in the audience, but as moderator, I get one question, and it's a very, very difficult question. What religion is Roberto Baggio?
Yeah, that would be Buddhism, I think.
Well, he's a true Italian soccer fan.
Yeah.
Baggio is a Buddhist.
Yeah.
Anyway, so thank you, Pierluigi. Great to see you again. Pierluigi, I haven't seen each other for a few months. So thanks everyone for coming along. Thanks everybody online. We could keep talking for ages, and there are many more questions, and I apologize for those online. We couldn't get to all of them. But thanks everyone, and we'll see you at our next talk that Carmen is giving.
Yeah.
She's preparing her talk at the moment, I think. Anyway, good on you. Bye-bye.
Thank you.